All right, cool. Let's keep going with this electrophilic aromatic substitution business here. All right, everybody take a second and tell me what my product would be of this reaction right here. These are one of our 5 electrophilic aromatic substitution reactions. We got to know those 5. So this attaches one of the cooler sounding functional groups here. What does this put on? A nitro group, one of those NO2 groups. Cool. So we got to know these 5 reactions, all right? But what we're going to learn here today is what happens when we mix and match them. So not just do one reaction, but now let's say that we followed this up with our halogenation reaction. Bromine and aluminum bromide is going to stick what on this ring? A bromine. All right, but now we got a question of where that bromine is going to go. We have 3 different possibilities here. It can go right next door to that nitro group. What do we call that position, the next door neighbor position? Ortho. So we could get the ortho product, or it can be one removed. What do we call that one? The meta product. Or it can be on the opposite side of the ring, and that one we call the para product. All right, and so the question is, which one of these is my product? Do we get them all? Do we get a few of them? You know, is there only one? What are the rules here? What's the deal? All right, so again, that's what we're going to talk. We talked about the individual electrophilic aromatic substitution reactions. Now we're going to take a few of them and we're going to mix them and match them, and we need to know what products are being formed. Okay, in this case here, it is only that meta product that you would get. Okay, so how do I know that? All right, so where we left off last time was looking at these benzene derivatives and taking a look at that group that's attached. And what we said is that certain groups are what are called electron donating groups. So these are groups where there's a lone pair located directly next to that ring. And as the name implies, what these groups are going to do is donate that pair of electrons to that benzene ring. Right? And so we illustrated that using these resonance structures here. In this first one, you can just see I am donating that pair of electrons to that ring, right? That's that first arrow that's been drawn. But I can't break carbon's octet rule, so that's going to kick this pair of electrons up onto this carbon. And then we just drew a whole bunch of other resonance structures here showing that pair of electrons being distributed around that ring. Okay? But what you'll notice is that pair of electrons, it only hits specific positions around that ring. It doesn't go to every single carbon, it jumps to every other carbon. All right? In these reactions, that benzene ring is playing the role of a nucleophile. So these electron donating groups are only going to make benzene an even better nucleophile, right? They're adding electron density to the ring. But again, they're specifically adding it to certain carbons. And so this is going to direct any incoming substituents to those specific carbons, okay? So these electron donating groups, I've highlighted in green here, where it's going to direct any incoming substituents. What do we call these next door neighbor positions? These are the ortho positions. Notice it skips that one removed, and what do we call the opposite side of the ring? The para position. So these electron donating groups here are what we call ortho-para directors. They will direct incoming substituents specifically to the ortho and para positions. All right, so then on the flip side, we don't have electron donating groups, but are what are called electron withdrawing groups. Okay, so a good example, one sort of common feature we're going to see in a lot of these electron donating groups, electron withdrawing groups, is a carbonyl carbon that's located directly next to the ring here. So on the flip side to what we saw to our electron donating groups, these are going to pull electron density from that ring. All right, is that going to make benzene a better or a worse nucleophile? So this is going to make benzene a worse nucleophile. So what we're going to see, practically speaking, is these reactions would take longer in the lab than if you just had benzene all by itself. So these create a worse nucleophile. These are much slower reactions. All right, and so again, a common feature, it's not going to be the only feature, but we're going to see this in a lot of them, are electron withdrawers. This sort of common feature that they're going to share is that carbonyl carbon attached to the ring. All right, cool. So let's use some resonance structures and some electron pushing arrows to show this group doing its electron withdrawing. All right, so now instead of adding electrons to the ring, we're going to pull electron density away from that ring. All right, but I can't stop there. What else am I going to have to do? Why can't I stop there? Let's start with that question. I got it. Too many bonds on that carbon, right? So the reason why that carbonyl carbon is able to pull that electron density onto itself is because it can kick that pair of electrons up onto that oxygen from that carbonyl bond, right? Oxygen, being very electronegative, is more than happy to accept that pair of electrons. I'm missing some important information here in my structure, the charges here. All right, that oxygen with its one bond and its three lone pairs should have what formal charge? -1. And I started out with a neutral molecule, so I better have this neutral resonance structure here. So what must be missing? Positive charge. And where is that positive charge going to go? Over here, right? This carbon in this process of getting that pair of electrons taken away from it, is left with that positive charge. Okay, and then we can keep going. Again, we can stabilize this positive charge by bouncing it around this ring through resonance.
Carboxylic acid have the same effect?
Yep, sure would. Yep. Anytime there's a carbonyl carbon, it could be an ester or a ketone, an aldehyde, as long as there's that carbonyl carbon directly attached to the ring. Yep. All right, so again, we're showing that this is an electron withdrawing group. It's pulling electron density away from that ring. We got this positive charge that we're bouncing around that ring through our resonance structures. All right, but again, what we want to notice is that that positive charge is not hitting every carbon. It's again just hitting every other carbon. So this one here, we'll map that onto our original structure. This one down here, and this one up here. Okay, so similar to what we saw before, we have this charge that's kind of being passed around this ring, but it's not hitting every carbon, it's hitting specific carbons. All right. But now I'm not having, unlike with my electron donating group, this was a lone pair. So a lot of electron density. It made those carbons even better nucleophiles. Now what I'm passing around this ring that I've lost, there we go, is a positive charge. So are these carbons going to be better nucleophiles or worse nucleophiles? They're going to be even worse nucleophiles, all right? So for our electron donating groups, they're going to donate, they're going to direct incoming substituents not to those ortho-para positions, because they've got those positive charges on them, but to those meta positions here. So these electron withdrawing groups are what we call meta directors. Those ortho-para positions have been destabilized by that electron withdrawing group. So anything new is going to be directed specifically to the meta position. All right, so let's just practice this real quick. If we take, for example, that phenol, and we perform our electrophilic addition reaction with bromine, everybody take a second and give me my products of this reaction. And then we're going to do the same thing, not with phenol, but with benzaldehyde. So how are we supposed to do this? Well, we recognize that that OH group is an electron donating group. And so that makes this an ortho-para director, which means that my incoming substituent is going to be directed either to the ortho position or the para position. We're going to get a mix of both products. All right, an ortho-para director, meaning that we get a mix of our ortho product and our para product. All right, notice that the bromine did not choose where to go. The incoming substituent isn't deciding where it's going to go on the ring. It's what was already attached to the ring that directs an incoming substituent to a specific position, right? The OH group is what decided, not the bromine that's being added. All right, and then on the flip side, this one we called an electron withdrawing group. These destabilize the ortho and para positions, making these meta-directors. So in the case of benzaldehyde here, when I do my subsequent electrophilic aromatic substitution reaction, it's going to direct that bromine to the meta position. All right, cool. So we have certain things that when they're on the ring, we consider them electron donating groups. So those are ortho-para directors. There are other things on the ring that we consider electron withdrawing groups. Those are meta-directors. All right, so now let's take a look at our big cheat sheet here of ortho-para versus meta-directors. All right, we're going to make this a little bit less scary to start out with. We'll go through these one by one. Okay, so we have what we call our strong activators here, meaning ortho-para directors. Again, we call them activators because they make benzene an even better nucleophile by donating electrons. All right, and what we just want to notice that all of these have in common is that lone pair located directly next to the ring, right? Signal of a activator, an ortho-para director. Okay, these ones here we consider to be our strong activators, and we'll talk about what I mean by strong, moderate, weak, etc. here in a second. All right, let's unveil our next category. These are also ortho-para directors, but they're considered to be more moderate. Okay. Now, we want to note, play the spot the difference game. The similarities, but also the differences between our strong and our moderate directors here. Okay? So first of all, they all still have that same common feature of that lone pair located directly next to the ring. All right? The big difference is what's on the other side of that heteroatom in each of these cases. On the left, I have my benzene ring. What do I have on the right, connected to those heteroatoms? A carbonyl carbon. And remember, those carbonyl carbons are electron withdrawing groups. So for these structures here, what you'll find is that you can draw resonance structures. Whoa, that's way too big. You can draw resonance structures where they're donating pairs of electrons to the ring. But there's also resonance structures that you can draw where that carbonyl group is taking some of that electron density away. All right, so these groups, they can donate their pair of electrons to the ring. They're just not as good at it because there's a carbonyl group on the other side pulling some of that electron density away. All right, this next group of weak activators. This is going to be the one, the exception to the rule here of our lone pairs next to the ring. All right. These are all alkyl groups here. Alkyl groups do not have any sort of electron donating ability. There's no lone pairs, but they have this weird property called hyperconjugation, where they can, again, make benzene a little bit weakly better of a nucleophile. So again, these alkyl groups are also orthoparadirectors. All right, we just got to be able to spy those as being orthoparadirectors. You'll notice it doesn't matter the degree of substitution. We got primary, secondary, tertiary. That's not relevant at all here. If there's carbons and hydrogens, that's going to be an orthoparadirector. Okay. Our next group, let's just take a look at them here. What do these all have in common? The halogens, all right? The halogens are also kind of a weird category. The halogens are orthoparadirectors. Notice how they have that lone pair next to the ring, okay? But they're considered to be weak deactivators, meaning they proceed slower than benzene. These halogens kind of have this push-pull going on. They have a lone pair that they can donate to the ring, but halogens are also extremely electronegative. So through something called induction, they're also withdrawing electrons from the ring. They're doing both at the same time. All right, now, if you go into the lab and you do these reactions, you will find that they are indeed orthoparadirectors, so we're classifying them as such. All right, and again, you can spy that with their lone pair next to the ring, but they react slower than our other orthoparadirectors because of this induction effect. All right, so this category here is our halogens, our alkyl, well, not alkyl, I guess, aryl halides. Okay, again, they can add electron density from those lone pairs, but they also withdraw electron density through what's called induction. All right, our next category. Well, let's just look at these ones first. What do these all have in common? That carbonyl carbon directly bound to that ring. So what do these makes these? Orthopara or metadirecting? Metadirecting, all right? So these are our moderate deactivators, our moderate metadirectors. Okay. Two more to note here. That sulfonic acid group is also an electron withdrawing group. You can also draw resonance structures, same as you can with carbonyl groups, to pull electron density away from that ring, as well as what are called nitrile groups, carbon-nitrogen triple bonds. All right, and we will see in a future chapter, nitriles are often lumped into the same category as carbonyls. Very, very similar properties. You have carbon with this high-level bond to a more electronegative element. Okay, and again, the whole idea being that these can withdraw electron density just like a carbonyl group. All right, the last category are strong deactivators, are strong metadirectors. This is the category that's kind of like the most memorization here, but it's a pretty small category. Importantly, our nitro group, we know how to make nitrobenzene, so this is an important one to note. Nitro groups are just about as strong of electron withdrawers as you could possibly have. The other one that we can make here, this one we won't see all that terribly often, but we're going to note it here. But this one is also important, all right? Carbon with a bunch of halogens on it. Why is that one so important? Because again, we know how to make this one, all right? Going back to our reactions at the benzylic position, if we take toluene and we put a boatload of that NBS in there, what we're going to do is replace every hydrogen in that benzylic position with a bromine. And again, this one is a strong metadirector. Right, a carbon with 3 halogens on it is a strong metadirector. Again, just one to kind of note, because like our nitrobenzene, we know how to make that. Cool. All right, so we have our master cheat sheet here of our orthopara versus our metadirectors. All right, and again, we have these classified as being either strong, moderate, or weak. We'll see why that matters here in a second. All right, for right now, let's just practice using these here. All right, we're going to take benzene, a normal benzene ring, and we're going to do not 1, but 2 electrophilic aromatic substitution reactions. My first one, I'm going to use fuming H2SO4, and then I'm going to follow that up with one of those Friedel-Crafts alkylation reactions. And then we're going to go into the lab and we're going to do the exact same thing, but I'm going to reverse the order. I'm going to do my Friedel-Crafts alkylation first and then treat it with the fuming sulfuric acid. All right, so everybody take a second, give me my products of these 2 reactions here. Again, we're going to see it depends on the order in which you carry these out, because certain groups are orthopara, whereas other groups are meta-directing. All right, so let's break this into these two steps here. All right, the first thing I'm going to do is treat it with that fuming sulfuric acid. That is going to put on that SO3H group, what we call a sulfonic acid group. All right, again, we just got to know these electrophilic aromatic substitution reactions, and you can see why it's really important, because now we're going to start mixing and matching them. All right, so that's my first reaction. Let me try to condense this a little bit. All right. In this next reaction, what am I going to be sticking onto that ring? CH3, right? A methyl group. All right, but the question is where? All right, so again, we got to look at what's already on the ring. The methyl group doesn't get to decide. It's what's already on the ring that's going to direct an incoming substituent to a particular place. Is this one of our ortho-para or our meta-directors? This is one of our meta-directors here. Much like a carbonyl group, it will pull electron density away from that ring. All right, so that means I'm just going to get my one product here. We don't know how to name these sulfonic acids, but I know it's my meta product. Cool. All right, so now we're going to do the same thing, but we're going to swap the order here. Now I'm going to do my alkylation reaction, my Friedel-Crafts reaction first, and then I'll add my fuming sulfuric acid afterwards. So now my first reaction puts a methyl group on that ring. And now I have my second reaction where I add that fuming sulfuric acid. Whoops. This intermediate here, we have a fancy name for. What's the name of this guy? Toluene. All right, cool. And toluene is what? An ortho-para or a meta-director? Remember, all of our alkyl groups are ortho-para directors. So this is ortho-para directing, which means that I'm going to have two products here. One where that SO3H group is right next door to that methyl group. And then another product where it is on the opposite side of the ring. All right, our ortho and our para product. Okay. Cool. All right. So we went through the trouble of labeling these as strong versus moderate versus weak. What the heck do we mean by that? All right. So let's just take a look at an example. Let me grab my pretty benzene ring. All right. On one end of this molecule, I'm going to put an OH group. And on the other end, I'm going to put a methyl group. And then I'm going to perform another electrophilic aromatic substitution reaction. It really doesn't matter which one you choose. You'd have the same effect. But nonetheless, I'll do this bromidation. Okay. so let's look here. My OH group, my hydroxyl group, what is that? Ortho-para or meta-directing? So this is ortho-para. It's got that lone pair. The para position's already occupied, right? But nonetheless, it would want to direct any incoming substituent to these ortho positions here. But what about my alkyl group? What is that? Ortho-para or meta-directing? That's also ortho-para. Which means it wants to direct an incoming substituent to the positions that are ortho and para to that alkyl group. So these positions right here, again, the para position's blocked off, but it wants to direct to the positions that are ortho to the alkyl group. So then which one is going to win here when I draw my product? All right, that's when our strong, moderate, weak business comes into effect. All right, if I look, those lone pairs directly next to the ring, those are our strong ortho-para directors, whereas those alkyl groups are considered to be weak ortho-para directors. All right, so not only can I say ortho-para, but this one's a strong, and this one's a weak. So what do we think wins, the strong or the weak? The strong, all right? So when we draw our product here, we're going to put that incoming substituent ortho to our strong ortho-para directors. All right, and again, our principle here is the stronger wins. All right, now sometimes your groups on the ring are in agreement. They both want to direct to the same carbon. All right, great, fantastic, no conflict. If there is a conflict, as in this example here, that's when that strong, moderate, weak classification comes into play. And again, whatever the stronger one is will win in terms of dictating the position of your substituent, your incoming substituent. Okay. So now, let's talk about our ortho-para product distribution. Okay, I'm going to warn you now that I'm going to straight up lie to you a little bit here. All right, this is what our textbook teaches us. I actually did a whole series of experiments in the lab last semester, and it turns out it's way more complicated than this picture we're going to paint here, but we're going to stick to our nice simple rules, and we can complicate things in the future here. All right, so we're going to look at our distribution of products when we take our phenol and we do our electrophilic aromatic substitution reactions. I don't know why, but in my mind I default to bromine a lot. You'll see I use that as an example for really no particular reason. I could have picked any of those five, all right? And we know that that phenol group, that hydroxyl group, is an ortho-para director. So we're going to get this mix of the ortho and the para product. Okay, so if we look at now the distribution of products, right? We carry out this reaction, we take our product, we put it on something like a GC, which will give us a readout of how much of each product we get. What we would find is we would have a distribution where about 66% of our product was that ortho product, and 33% of that product was our para product. All right, so we get about 2/3, twice as much of the ortho product as we get of our para product. All right, why might that be? Anybody have a guess? What's up? Boom, awesome. There are twice as many ortho positions as there are para positions, right? So if I stuck my bromine here or here, I would have my ortho product. And there's only one of those para carbons, right? So it's just a numbers game. If you're randomly sticking stuff somewhere, you have twice as much of a chance of putting it in the ortho position as you do of the para position. Okay, so we can just simply say, why do we have this product distribution? Twice as many ortho than para positions. Okay, but now we're going to take this same molecule here. We're just going to change it by making, instead of a hydroxyl group, instead of an alcohol group, we're going to make it an ether by sticking a whole bunch of carbons on there. All right, we're again going to perform our same electrophilic aromatic substitution reaction. This is still an ortho para director, still has that lone pair next to the ring, strong activator here. All right, but now if I run my sample on my GC to get my product distribution here, I'm going to find that we have something more along the lines of 95% is my ortho product, and only about 5% is that para product. A really dramatic shift from what we saw previously, where the major product was the ortho product. All right? So what's different about this one that will help explain why we got so much less ortho product? It's not the bromine size, right? It's the other thing size. It's this ether group on here that's big and massive and preventing these bromines from accessing that ortho position. We have a fancy name for this kind of effect. This is what we call steric effects, right? The idea that two big things don't like being next to each other in the world of chemistry. Okay, and we have like kind of a helpful little cutoff that we use for groups with more than 3 carbons. We have that steric effect that dominates, and we get majority of our para product. Or we can say para product is our major product. Okay, so if we have a small substituent on that ring, we have this effect where we just got more ortho sites than we do parasites, so that ortho product will be our major product. But if we stick something big and bulky on that ring, it's going to block that ortho position, and we're going to get a majority as our para product instead. Cool. Break. That's all I got for y'all.
So for